appreciate your attention and participation. My name is Zijun Ke from Sun Yat-sen University at Department of Psychology at Sun Yat-sen University. And most of my work actually centers on Mason, so meta-analytic structural equation modeling. And I have several papers on that topic. So that's why I'm giving a workshop on meta-analysis. And I have also conducted several like substantive meta-analysis, and some of which come out in journal like Nature Human Behavior and the Journal of Applied Psychology. And I'm also interested in non-experimental causal modeling. So if you have any questions about today's material or about meta-analysis in general or about causal inference, don't hesitate to email me later. Okay, and let's look at today's workshop. So basically, this workshop consists of three parts. Um, and we will start with the fundamental concepts and the critical threat of publication bias. Let me Okay, and in part two, we will tackle the specific statistical tools to detect and correct publication bias and how to handle complex data structures simultaneously. And in part three, we will have some live R coding demonstration and practice. Um, so here is the roadmap of the part one. So first, let's think about the question. So why do we need meta-analysis? And maybe we can think about this question from the maybe the perspective of meta-analysis, what meta-analysis can do. And this will help us to understand the importance of meta-analysis. So first, maybe we want to map the research domain. So we know that in many research fields, thousands of papers are published every year. So it is generally impossible for every researcher to read and digest and organize all of those papers. And then the meta-analysis, it would give us an objective, quantitative and transparent lens to see the big picture, and it helps us to establish scientific consensus and track how findings evolve over last decades. And second, maybe we want collective results. And we know that individual studies, especially psychological studies, often suffer from small sample sizes or low statistical power. And then if we can pool or aggregate those scattered evidence together into a single summary result, we may dramatically increase our statistical power and precision. And third, maybe we want to compare subsets of results. And we know that science is rarely one size fits all, and studies differ in, for example, how they measure variable and how they design the experiments, and who their participants are. And through like heterogeneity analysis or subgroup analysis or meta regression, um, we may seek the answers to questions like, okay, why do some studies they find like strong effects and the others find weak effects? And this is the true power of meta-analysis. Okay, so before we go into really the meta-analysis, we face a very a major challenge. We know that different researchers, okay, they will use different scales. So, for example, one paper they want to measure the depression, they may use a 10-item scale, and the others study they might use 20-item scale. And the third study they might use like clinical diagnosis. Then how do we compare apples to like oranges? One way to solve this issue is to compute or convert everything to a common metric called effect size. Here we use yi to denote effect size. So an effect size would standardize all the findings across different studies using different metrics or scales and putting everything on the exact same statistical footing. But depending on your specific research objective, the metric you use will vary. If you are looking at like single variable metric, uh, then maybe you would like to use like the sample mean, sample standard deviation, response ratio, and etc. And if you're interested in, for example, how two variables are correlated with each other, then maybe you would like to use like Cohen's d, Hedges g, Pearson's correlation, odds ratio, or risk ratio. Or if your research is more advanced, maybe you want to use like multivariate meta-analysis or Mason, so the meta-analytic structural equation modeling, like to test or examine the complex relationship among multiple variables. So no matter how complex it gets, the foundation always starts with a clean standardized effect size. So once we have our effect size, a crucial question arises. So how should we compute so, or should we treat every study equally? Imagine that we have two studies. So study A is a massive multi-site project, and we have 5,000 participants. And study B is a small pilot study. We only have 15 undergraduate students. And intuitively, you know that, okay, study A is more trustworthy and reliable than study B. So the difference is captured by sampling variance, denoted by like VI or SEI squared, or standard error squared. So a larger sample size, MI, so leads to a smaller sampling variance, VI. So this also gives us a higher precision. Therefore, the core logic of meta-analysis relies on what we call inverse variance weighting. So the weight give to any study, so that we use WI to denote the weight we give to any study, is calculated by 1 divided by VI. So this means that studies with small variance get huge weights, and studies with huge variance gets very small weights. We admit that actually we have other weighting methods. For example, the sample size weighting. This is very common in management and psychology, and sometimes we call it like Hunter-Smith approach. But inverse variance weighting is still the gold standard. Okay, so no matter which weighting method you use, so ultimately the meta-analysis is doing like we are calculating some sort of average. The difference is merely like how you compute the weights. So that's for meta-analysis synthesis. And when we calculate this weighted average, we need to choose between two main statistical frameworks. So first one is the fixed effect model, and the other one is the random effects model. So let's break down carefully because choosing the right model is crucial. So under the fixed effect model, we assume there's one single true effect size hiding out there in the universe in every study, just like the plot on the top right. Every study in the meta-analysis is trying to estimate the exact same number. And any differences we see between studies are assumed to be caused entirely by sampling error, random sampling error. So we use EI to denote the random sampling error. And theta here, we denote the one single true effect size behind the observed effect sizes. But let's think about in the context of psychological studies. Is that realistic for like psychological studies or social sciences that we all assume does the same universe true effect size? Like think about like researchers in Beijing, London, and New York. They all study the exact same psychological phenomenon, and will they get the exact same result? Probably the answer is not, right? And different cultures, we know that different age group or slightly different experimental procedures and different operational definitions, or they might cause the results to be divergent. So this brings us to the Brandon effects model, which is almost always preferred and more realistic choice in social sciences. So under random effects model, we assume that the true effect size across studies following a normal distribution. So here, let's see the equation here. Um, all those true effect size, we use theta I to denote the true effect size from study I. So we assume that it follows a normal distribution with a mean mu theta and a variance between study homogeneity uh, that is tau squared. And because the model changed, so the weighting also change. So in a fixed effect model, we only have one variance source that is sampling error, VI. But however, in random effects model, the model sources has two parts. So one is due sampling error, and the other one is our between static homogeneity, tau square. So consequently, the random effects model, the weight is now computed as 1 divided by here vi plus tau square. And because we add tau square into the denominator, then the weights become more balanced. So small studies would not get completely crashed by massive studies. Therefore, unless you have a very specific theoretical reason, otherwise always default to the random effects model for real world psychological data. Okay, now we understand the basic meta-analysis models. Then how do we actually conduct meta-analysis from scratch? So it follows a strict, transparent workflow. So basically, we have like one, two, three, four, five. We have five steps to go through. And what I want to emphasize here is that when searching for literature, so in the second step, when searching for literature, we cannot just look at one database. So we need to use broad databases like PubMed, PsycInfo, Web of Science, and etc. And also, there's a critical warning. So if you only search for like published journals, your meta-analysis may be deeply biased because of the this is because of our the central topic of today's workshop, that is publication bias. So to fight for the publication bias, to fight against publication bias, so we recommend you also searching for great literature, such as the doctoral dissertations on ProQuest or preprints on servers like PsycArchive. And dissertations and preprints often contain non-significant or null results that never make it to like get published to traditional journals. And furthermore, to ensure complete scientific integrity, modern meta-analysis require pre-registration. So you should register your protocol beforehand on platforms like OSF, registries for social sciences. And pre-registration ties your hands up because it prevents p-hacking and stops selective outcome reporting and proves to reviewers that you didn't change your inclusion criteria, for example, halfway through. And here are some links that might be helpful when you really perform a meta-analysis. Now, um, let's go to the center topic of today's workshop, that is publication bias. So, what is publication bias? It is actually the systematic distortion of the publication literature, where the studies that actually manage to get published are completely underrepresentative of all research that was actually conducted. So back in 1979, Robert Rosenthal gave this a brilliant and famous name, the file drawer problem. So imagine a researcher runs an experiment. If they find a statistically significant result, so basically we have p-value smaller than 0.05, they will celebrate and write a paper and send it to a high impact journal. But what happens if they find a null result, which means we find a p-value greater than 0.05, or we find a counterintuitive result? Then most of the time, we will get discouraged and they will throw it into their physical or digital file drawer and never look at it again. So what drives this systematic distortion? So the first one, probably the editors and reviewers of the some traditional journals, they would love novel, clean, statistical significant findings. So they rarely want to publish papers saying we find no effect. But things are getting better nowadays. And the second source of the second source of drivers of publication bias is career incentives. So under the brutal academic pressure, researchers' careers depend on getting positive results. So that's why you can see only positive results. And the third one is the commercial conflicts of interest. For instance, some companies or corporate sponsors, they might suppress trials that show their product doesn't work. So that's why we will have publication bias problems. But uh, eventually you might wonder, so how bad it is in practice. So let's look at the hard data. So in a study by Fanelli in 2010, this paper find that psychology and psychiatry actually is the worst offenders across all sciences. They actually find that 91% actually of the published papers in psychology and psychiatry reported positive and significant results. So to put that in perspective, psychology was 5 times more likely to report p-value smaller than 0.05 findings compared to space sciences. And space sciences is a field that doesn't care about like positive findings, positive results. And looking at the striking evidence from Skill and colleagues in 2021 regarding registered reports, they found that in standard journals where results dictate publication, 96% of papers reported positive results, but in registered reports where journals agree to publish the paper before, okay, they see the data, then, and purely based on the quality of the design, then the positive reporting rate dropped to 44%. Well, the large discrepancy between these two numbers is an indication of a severe publication bias in our area. And I think probably this severe distortion is one of the reasons why we observe the so-called replication crisis in 2015 by the Open Science collaboration. So when a massive team, they attempt to replicate 100 high-profile psychological studies, they found that only 36% of them successfully replicated. Only 36% of the famous psychological experiments were replicated. And even worse, the replicated effect sizes were half the magnitude of the original one. I think on average, the original one is like around zero point 0.4, the effect size. However, in the replicate studies, then the average effect size drops to I think zero point 0.2. So we can see how publication bias inflates our literature and creates false positives and misleads the entire fields. So, so now how can we detect this threat visually before we even run complex statistical models? We may use a diagnostic tool called funnel plot. So first, let's look at how to read the funnel plot. So in a funnel plot, on the x-axis, we plot the observed effect sizes. And on the y-axis, we plot the precision or the reciprocal of the standard error. And then we will see that the data points with high precision, then they will sit at the top. And the data points with low precision, so we have large standard errors, then they will sit at the bottom of the plot. And if there's no publication bias, which is as the plot on the bottom left, then we can see that studies scatters evenly and symmetrically around the true summary effect. And the data points will give inverted symmetric quorum. So why the quorum? Why the quorum shape? Because small studies at the bottom, they will have large sampling variance, so they scatter widely. And large studies at the top, they will have lower variances, so they cluster tightly near the center. So that's why we have a quorum shape. But look at what happens when publication bias is present. So which is shown on the right. So because small studies with negative or null effects are left sitting in the file drawer, so we cannot see them. So the bottom left corner of the plot is completely empty here. You can see that. So this will create a symmetry. So what we call a missing trunk here. When you see this asymmetry funnel plot, then this is an alarm telling us that publication bias has severely distorted our data set. And to wrap up our first part for today's workshop, so remember that meta-analysis relied fundamentally on inverse variance weighting, and always prefer random effects model to properly account for real-world heterogeneity across studies, and combat publication bias at the very source by combining rigorous pre-registration with extensive grade literature searches. And thank you very much for your patience and attention for uh, uh, part one. And let's take a 5-minute break. And we will resume with part two in 5 minutes. And in part two, we'll discuss specific statistical tools to detect and correct for publication bias. So let me stop sharing my Oh, hi everyone. Welcome back to the second part of our today's workshop. In part one, we covered the fundamental definitions of meta-analysis and learned why inverse variance weighting is our gold standard, and discussed why random effects models are almost always preferred over fixed effect models. Well, that's because real world true effects naturally vary across like different studies and settings and for different populations. So we also expose the dark side of our literature, so publication bias and the fire drawer problem. And in part two, we're going to dive deep into the more advanced statistical toolbox, and we will learn how to detect publication bias statistically and how to correct for it, and how to handle complex data structures, especially when studies report multiple dependent or correlated effect sizes. So after this theoretical section, we will move on to part three for our live R coding and demonstration. And by the end of this workshop, I hope that you won't just understand the math, you will also know how to run these cutting edge models yourself. So let's take a look at the roadmap of for part two today. Um, so we will basically for this part, we will start with the classic method first. So which is the Agar's test. Basically, this is a simple regression method to check Fresnel asymmetry. And then we will move on to the PET, and method. And this is a regression-based correction tool. And next, we will set up to selection models and focusing on the one of the selection model that is the three parameter selection model. And this method would explicitly models how studies are filtered based on their p-values. And finally, we will tackle the modern Bayesian extensions, especially robust Bayesian meta-analysis, or RoBMA for short. And RoBMA is a breakthrough approach that solves complex issues like dependent effect sizes and publication bias simultaneously. And think of this section as a progression from classic, intuitive tools to modern, robust methodologies. So now let's start with the classic method that is Agar's test. And this method is introduced by, I think, probably Matthias Agar and his colleagues in 1997. And the core logic of this method is very intuitive and simple. And as we mentioned in part one, in a Fresnel plot, small studies with large standard errors, they will sit at the bottom of the Fresnel plot, while massive studies will sit at the top. So if there's no publication bias, then we will see that small studies they will scatter symmetrically around the overall effect. But if small non-significant studies are missing, then the bottom of the plot they will lean heavily to one side, and then we will have a symmetry funnel. Then Agar's test, they relied on regression model to systematically evaluate the asymmetry. What they use is the weighted regression. So specifically, we regress the effect size, yi on its standard error, SEI. So this is the weighted regression equation for Agar's test. And in this equation, if the slope, so beta 1, is significantly different from 0, and this would be an indication of funnel asymmetry. It also signals that potential will probably have publication bias in our data sets. And if you look through different meta-analysis textbooks or handbooks, you may encounter a seemingly different mathematical version of Agar test, often presented in ordinary least squares forms, which I presented here at the lower part of this screen. Um, this alternative version, um, they actually regress not the original effect size yi, but regress the standardized effect size. So basically, we divide the original effect size by its standard error. So we use zi to denote the standardized effect size, and we regress this standardized effect size on its precision or the reciprocal of standard error. So it is important to know that if you use OLS form of Agar's test, then we don't test whether the slope of the or the slope the regression coefficient of SEI, whether the slope is significant from zero, but we test actually the intercept, whether the intercept is statistically significant from zero. And if we have a non-zero intercept, then this is an indication of a potential publication bias. So why is Agar's test so widely used? Well, partly because it is fast, intuitive, and easy to interpret it. However, it comes with several severe limitations that every researcher must keep in mind. So first, it has a high positive rate when between study heterogeneity, that is tau squared, is large. So for example, imagine a meta-analysis on psychotherapy. And small studies, they might use intensive high dose inpatient settings, and they will get large effects. While large studies, they might use low dose outpatient community settings, then they will get smaller effects. And here, and this asymmetry is driven by real clinical differences and not publication bias. However, if we use Agar's test to inspect this data set, then we will then Agar's test might falsely flag that publication bias is present. This is why some researchers believe that Agar's test actually examine the so-called small study effects and not necessarily the publication bias. And second, Agar's test suffers from structural mathematical artifacts. For certain metrics like standardized mean differences, for example, Cohen's d, or log odds ratios, the standard error is mathematically tied to the effect size itself. And this built-in correlation triggers false alarms, even when zero publication bias exists. So if Agar's test detects publication bias, then how do we correct for it? A popular regression-based solution is the PET-PESE. Let's break down this very complex name of the methods and understand what they mean and how they work. So first, the PET stands for Precision Effect Test. So it uses a linear regression of the effect sizes on the standard error. So the model for PET is like this. So yi equals alpha 0 plus alpha 1 times SEI plus EI. And take a look at the intercept here, so the alpha 0. So what does it actually means? So actually we interpret the intercept of regression in that, so when we have our predictor takes a value of 0, so the expected outcome value is what the intercept means. So basically here, the intercept means when we have zero standard error, the expected effect size we will get. So that's the intercept alpha 0 here. But what does it mean when we have a standard error of 0? Then this means that we have an infinitely large study. And in an infinitely large study, the sampling variance, the sampling error vanishes, and publication bias also has no effect because we have the population, right? So that's PET, PESE method, they believe that this intercept is the true effect cleared of publication bias. So that would be the corrected estimate of the mean effect. And next, we will have the PESE method. PESE stands for Precision Effect Estimate with Standard Error. And it works similarly, but uses the variance, so SEI squared instead of standard error to form a quadratic curve. And if you look at the extrapolation plot right here, okay, right here on your screen, you can see both models in action. So the red line here is the PET, and the blue dashed curve is PESE. And both extrapolate down to SE equals 0 on the left axis. And this is for us to estimate the true underlying effect. So now why do we need two models? So both PET and PESE? The reason is that the author of this method, so Stanley, and he believes that PET regresses FSS linearly on its standard error. And it only works wonderfully when the true effect size is 0 or very close to 0. But when we have a general and non-zero effect, then PET suffers from a major flaw. That is, it tends to overcorrect and downwardly bias the true effect size. You know that we want to get a significant result, right? We don't want a non-significant result. So that's why Stanley, he think that we need PESE. So instead of using standard error, PESE would regress effects on their variances. So if we look at the blue line here, then you can see that the blue line would not drops too far when it extrapolating back to 0. So then it would not overcorrect the true effect size. So this clever adjustment would prevent the over correction problem and yields a much less biased estimate when we have non-zero effects in the population. So that's why we have two parts of this method. But how do we apply PET, PESE in practice? And Stanley established a clear two-step decision rule. In step 1, we run PET model first, and then we check whether the PET intercept alpha 0 is statistically significant. And if it is significant, then it tells us that a true non-zero effect exists. However, as we mentioned previously, PET tends to underestimate the true effect size. So then we need to switch to PESE and use the PESE intercept, so beta 0, in the previous slide as our final bias corrected effect size. And in step 2, if the PET intercept is not statistically significant, then we stay with PET and concluding either the true effect is 0 or that the field is entirely driven by bias. And I want to emphasize here that both models use weighted least squares and weighting each study by its precision or the inverse of its variance, the sampling variance. Okay, now let's look at the limitations of this method. So despite its widespread popularity, PET, PESE does have some critical vulnerabilities, okay, that we need to keep in mind. So the first one is that it performs quite poorly in small meta-analysis. So typically, when the number of studies is less than like 10 or 20, in these small samples, the statistical test for the PET intercept completely lacks power. So it's very hard for you to find a significant PET intercept. So then the decision rule will forces you to stick with PET instead of switching to PESE, then which ultimately will leave the true effect size severely under-adjusted. And second, and perhaps the most important, and PET-PESE suffers from severe over correction when high heterogeneity is combined with small sample sizes. So let me emphasize this. So heterogeneity by itself is a little bit tricky. Um, the problem comes much worse when it combined with small samples. So when study results vary widely due to real methodological and contextual differences, um, meaning our tau square is very high, and we also have a small number of studies. The regression line will get heavily distorted, and this distortion rejects the intercept dramatically downward and sometimes artificially forcing a general positive size all the way down to zero or even into the negative territory. So if your research field deals with high heterogeneity and a limited number of studies, then use PET-PESE with the extreme portion. And for the second limitation of PET-PESE method is that as we mentioned previously, it's also a regression-based method. So then it would have similar issues as does the Agris test. So it is still vulnerable to subtle mathematical structural trap. So, for example, let's look at the formula for the sampling variance for of Cohen's d at the bottom of the slide. We can see that, okay, the d squared is inside the sampling variance equation. And this means that when the effect size, so d here, it gets larger, then the standard error or the sampling variance will also increases. Then we will see a mathematical dependency between sampling error or sampling standard error or sampling variance and the effect size. And because both PET and PESE, they rely on regressing the effect size on the standard error or sampling variance. So this inherent structural correlation would completely trick the model. And it leads the model to detect false signals of bias and resulting in a remarkably high false positive rates, even when the underlying literature actually is completely clean and bias-free. So this is the second limitation of PET-PESE. So now let's look at a completely different class of method, that is the selection model. And specifically, we will look at the three-parameter selection model. And this method is developed by Vivier and Hedges in 1995. And this method, instead of drawing a regression line or quadratic curve, uh, the selection model method, they will explicitly models the filling mechanism of publication. And they would use the step functions. So what is step function? Specifically, it divides the range of p-values into multiple distinct intervals. So for example, we can divide the p-values at standard thresholds like 0.05, 0.025, or higher. And it then assumes that a study's probability of being published is constant within each interval, but can jump or drop across intervals. In other words, it estimates the relative publication probability for each specific p-value interval. And the selection model methods, they will simultaneously estimate three types of parameters. So the first one is our mean true effect size. We use mu theta to denote it, mu theta here. And also the second type of parameters is the between study congruity. We use tau squared to denote it. And the third type of parameters is selection weight. We use omega j. We use omega j here to denote it. So omega j represents the relative probability that a non-significant result gets published compared to the significant one. So here j represents the j's p-value interval. So to put this into perspective, so omega j, if we have a omega j of 1, so this means that the publication is unbiased. So we have the non-significant results are just as likely to be published as the significant ones. So if we have a omega j of 0.2, this means a non-significant study has only 20% chance of being published compared to the significant one. So I want to point out an important technical detail here. It is entirely possible to attain an estimate of omega that is greater than 1. So why does this happen? Because 3PSM, so the pre-parameter selection model, actually estimates a relative rate rather than an absolute publication probability. To ensure model identification, the selection model method would fixes significant results, meaning studies with p-value smaller than 0.05 or 0.025, to have an omega of 1 as our baseline. And all other omega values are relative to that baseline. So therefore, if your meta-analysis happens to contain like more non-significant results than significant results, then you are very likely to attain omega estimates exceeding 1. In fact, actually, we will see this exact scenario in our part 3 R demonstration. Now, so let's see how we actually test for publication bias using the selection model method. In the selection model method, we usually use likelihood ratio test to compare two competing models to detect publication bias. So the first one is the unadjusted model. So basically, this would be our standard random effects meta-analysis model, and in which we assume that publication bias is absent. So meaning that all selection weights or the relative publication probability parameters omega j, all of them are equal to 1. And the other model is the adjusted model. And this is the full selection model. In this model, we would incorporate the estimated selection weights across our p-value intervals. And by comparing these two models, we can see whether there is publication bias. And we would use chi-square test statistic to compare these two models because they are nested models. So the decision rule is that if the chi-square test is significant, then it tells us that adding selection weights to the model will significantly improve our model fit. Then this provides strong statistical evidence confirming that publication bias is present. And in this case, we should report and adopt the adjusted model. And if the test is non-significant, it means accounting for publication bias doesn't significantly improve the model fit. then therefore we will stick with the standard unadjusted model. So that's the decision rule for how we use a selection model to detect publication bias. Now let's look at the limitations of the selection model. While 3PSM is radically elegant, traditional maximum likelihood estimation has major practical limitations. Here we summarize these challenges into three major bottlenecks. So let's first look at the first one, the small sample instability. The 3PSM typically requires a substantial number of studies, at least 40 to 60 studies, to have precise omega estimates. When these estimates are imprecise, it can severely distort our estimation of both the mean effect size and the heterogeneity, and ultimately leading to misleading inferences. So in practice, if you have a small sample, say 10 studies or fewer, the model frequently fails to converge in R. And that's the first limitation of 3PSM method. And the second limitation of the 3PSM method is the rigid selection cut points. And the standard 3PSM defaults to one-sided boundary at p equals 0.025. So if a specific research field operates under different thresholds, the model will become misspecified. And then we will have misleading results. And this plot on the right demonstrates how the weight function operate under varying selection severities using the Vivier and Woods sensitivity framework. So the horizontal axis here displayed one-sided p-value intervals, and the vertical axis here shows relative publication weights. So the solid blue line here represents the moderate selection model, where non-significant results still retain, so we can see here, it still retains around a 50% chance of publication. And the dashed orange line here, it represents the severe selection situation, where studies with like p-values greater than 0.5 have less than, I think, less than 40% chance of publication. And this would attenuate the mean effect size down to, and actually, in a paper in the Mertens 2022 PNAS paper, they test their data by assuming both the Boole moderate selection model and the orange line, the severe selection model, and they find quite different results. When they assume a moderate selection publication bias, then they would find their estimate of mean effect size is around 0.3. And if they assume a severe selection pattern, then the mean effect size would drops to only 0.08. So this would make quite different results regarding the mean effect size. So what makes this critical is that the different selection cut points and omega weight setting would yield quite different mean effect size estimates. And in actual empirical analysis, actually we never know the exact underlying publications, selection mechanism, and severity. So this uncertainty would dramatically impact the meta-analysis results. So that's why the limitation of the traditional three parameter selection method is that you cannot balance like the results from different selection cut points settings. So that's the second limitation of this method. Um, and the third limitation of the method is that um, the traditional selection method, they assumes every effect sizes comes from a completely independent study. And this brings us straight to a major structural challenge in modern meta-analysis. That is the correlated effect size or dependent effect sizes. But before we explore modern solutions, let's clearly define what dependent effect sizes are. So in real-world research, a single paper rarely yields just one independent effect size because it's very hard to get published. And dependency typically arises in three scenarios. So the first one is multiple treatment conditions. So for example, a paper may compare two active treatment, for example, the cognitive behavioral therapy or mindfulness-based intervention against a single shared control group. So for example, the waiting list group. And both calculated effect sizes share the exact same control participants. And this would create statistical dependency. And the second scenario is multiple outcome measures. For example, a study may evaluate anxiety using three separate questionnaires. So, for example, the generalized anxiety disorder, the state trait anxiety inventory, the back anxiety inventory on the same paper. So, is there anything happen?
Yeah, the image is small.
The images, yeah, I know, but it
Yeah, it's
is
restored
my
back.
slides. Oh, okay. So, and then in all those cases, the resulting effect sizes inherently correlated because they originate from the same groups of participants. So, if we ignored this nested or dependent structure, and that would break the fundamental assumption of the traditional selection models. Um, um, then we would have misleading conclusion, biased estimates. So that's why we need to address the dependency. And it is a very critical step before we move on to modern alternatives. So let's look at what happened if we fit those correlated or dependent effect size into three PSM. Basically, as we mentioned before, it will violate the core assumption of independence. And this plot here actually shows how it would bias the result of the 3 PSM. So we can see that the dash line here, the horizontal dash line at the 0.05, this is our nominal type 1 error rate. And the results of this plot, actually, they all come from simulated data sets with no publication bias. And actually, the result, this plot actually plot the rejection rate or the significant result from the chi-square test of the 3 PSM method. And we can see that when there's no, even if there's no publication bias, but the actual false positive rate here represented by color lines, they all of them, they are well above the nominal level, like the 0.05 level, the 5% level. So some of them are 20, 30, or even 40%. And we can see that as the true effect size increases, the terminal rates actually would grows. So basically, this result tell us that uh, the traditional frequentist selection model will constantly flag publication bias simply because multiple data points are clustered, even if there is no publication bias. So that's why we need to handle the dependency of the effect sizes. And what's more important, the dependency doesn't just ruin the detection of publication bias, it also corrupts the correction, publication bias correction as well. If we look at uh, the very recent paper by the Bartosz to 20 this year's paper, and they found that the traditional selection model, they confound the within and between study variances because they ignore the hierarchy structure of the data. Then uh, this means that the traditional method would assume more independent information than is actually there. Then it would underestimate the standard errors. So we would get narrow confidence intervals. And furthermore, and because we ignore the hierarchical structure of the data, um, and it would actually distort our mean effect size estimation. In their simulation study, they found that the traditional 3 PSM method would tend to overestimate the true effect size. But I want to emphasize that this finding is solely based on this very paper. But in our demonstration, we will find that in the data set we use, actually, uh, if we ignore the effect size dependency, actually we get um, the traditional method actually would tend to underestimate the true effect. So I think both directions are possible. But the key point here is that if we ignore the dependency among effect sizes, we would attain bias estimates. So that's third solution, the third limitations of the traditional selection model method. So then how do modern methods solve these challenges? So let's look at two practical solutions. So the first one is the fixed weight sensitivity analysis, and the second way is the robust Bayesian meta-analysis method. So now let's move on to our first solution, the fixed weight sensitivity analysis. So as we know that forcing maximum likelihood estimation to simultaneously estimate selection weights often fails, especially in small data sets. So to overcome this issue, then our approach is straightforward actually. We can fix the weights, denoted as omega j, a priori based on standard predefined scenarios. So for example, the moderate or severe publication bias. This would allow us to test whether our substantive conclusions still hold under some extreme conditions. So let's walk through a fictitious example to see how this works in practice. So first, look at the ideal scenario on the left here. Here, our unadjusted effect estimate is about 0.45, 0.4. And if we apply the severe bias weight, so for example, we assume that for non-significant results, there are only 20% of getting published, 20% chance of getting published, then our estimate would slightly drops to 0.32. And more importantly, we will find that the confidence interval, okay, with the severe publication bias specification, uh, the confidence interval still stays well above the zero line. And this tells us that our finding is robust. Okay, this is the ideal situation if we perform the sensitivity analysis. Now let's look at the unideal scenario on the right. Here, the unadjusted effect size estimate is 0.35. But if with moderate bias correction, so for example, if we assume a moderate bias, so for example, we set the omega j for non-significant results to zero point 0.5. So non-significant result now has only have only a 50% chance of getting published. Then our mean effect size estimate now would drop to 0.08. And then our confidence interval now would cover 0. And under severe bias specification, the effect even flips negative to negative 0.05. And this unideal scenario, this revealed that our finding is highly sensitive to publication bias. But what if we encounter this situation? If a sensitivity analysis shows that our conclusion can be easily overturned by mild or moderate bias, uh, we cannot simply ignore it. There's a few options for us to do. So the first one we may we may explicitly report the exact level of publication bias required to invalidate our findings. And second, we may contextualize our evidence. So for example, we can frame the effect that we find as conditional on the absence of severe selection bias. And third, we may explore alternative specification. For example, we can check whether subgroup analysis, alternative estimates, or incorporating more study level covariates can stabilize our estimate. So in this way, the sensitivity analysis would shift from being merely a diagnostic tool. Um, it would help us to become more transparent and honest. And that's for our first modern solution to the challenge that we face. Our second solution is the robust Bayesian meta-analysis, or ROBMA for short. ROBMA for short. And when dealing with the publication bias and complex data, a common pitfall is relying on a single rigid statistical model. So this ROBMA, they takes a fundamentally different and much more robust approach. This method use Bayesian model averaging. Instead of putting all our eggs in one basket, RoBMA fits a massive ensemble of models, combining normals, traditional PTPSE models, and selection models all at once. So it can weight and average them, all those models, based on how they actually fit the data. So basically, they use the posterior model probability to as the weights to compute the Bayesian model average results. So then you can figure out, so you don't need to worry about, oh, okay, which model is the best model. So you don't need to make the difficult decision. But the most exciting part of this method is that the very recent extension allowed this method, the RoBNA method, to incorporate three-level structures, which means that it can handle dependent effect sizes and publication bias issues simultaneously. To see why this is powerful, let's look at the three-level uh, uh, rho BMA model. So how does this model manage dependent effect sizes? So basically, this model would decompose the total variance among effect sizes into three distinct levels. So let's work through them one by one. So the first level is the sampling level. And this level, the variance in this level, we call it sampling variance. We use Vij to denote this variance. So this variance will capture the pure sampling error within individual effect size estimate. And the second level is the within study level. And the variance in this level, at this level, we call it within study variance. So we use tau W squared to denote it. And this variance captures the variance between multiple effect sizes nested within the same study. So for instance, when a paper reports multiple correlated outcomes, then tau W squared is used to describe, okay, how different they are. And the third level is the between study level, and the variance in this at this level, we call it between study variance. We use tau b squared to denote it, and this variance captures the variance between entirely different studies in our meta-analysis. Then, by cleanly separating these three levels, the model stops confusing study clustering with publication bias. Then, uh, when because RO BMA method is very powerful in incorporating this three-level model simultaneously with the, for example, the selection weight uh, to describe the publication bias mechanism. So rho BMA method can achieve something traditional methods struggle with. So it can stabilize, okay, our estimation when the number of studies is relatively small by using some weakly informative price. And also, it can account for second modern solution to the challenges we face. Um, And now let's take a step deeper and look at the math and how exactly does the three-level model account for dependency mathematically. So let's look at the model specification in the collapse form here. So basically, our effect size Yij equals the mu theta plus uj plus zeta ij plus eij. So let's break down this individual parts so that we can understand what those parts means. So first, this mu j, it means the overall effect size. Not mu j, mu theta. It denotes the overall effect size. And then the second term is uj. This means this is the effect size. The effect size within study J, what they share. This is the random effect they share. So we use uj to denote the random effects that shared by effect size within study J. And zeta ij actually captures the within study deviation. And finally, we have eij. This represents pure sampling error. So basically, and so basically, multiple effect sizes from one study, they share the same term, that is uj. And this would cause those effect sizes to be correlated. So for example, we can compute, based on this model, we can compute the covariance between any pair of effect sizes from the same study. So basically, we can compute like the Yij and Yi prime j. So these two effect sizes are from study J. And if we compute the covariance of them, then we will find that the covariance equals to tau b squared. So then we can see that these shared random effects uh, create the dependency, create covariance. So then if we divided the covariance by the variance of the total variance, then we will attain the intra-study correlation, uh, which is here, row within. So it is also very informative to look at how different frameworks choose to parameterize these variances. So if you're familiar with the traditional package-like metaphor in R, they typically fit a three-level models like this. Uh, by estimating, okay, the within study variance, so tau w squared, and the between study variance, so tau b squared, as separate parameters. But the robust Bayesian meta-analysis, they takes a slightly different path, okay? Um, they actually parameterize the model by estimating the total variance. So basically tau b squared plus tau w squared. And they estimate the intra-study correlation, which is defined as uh, the tau b squared divided by the sum of tau b squared plus the sum of tau b squared and tau w squared. So basically, robust Bayesian method meta-analysis and the traditional meta-analysis software like Metaphor, they use different ways to parameterize the three-level model. So this is what we need to keep in mind when we use those different software. Oh, I think I'm stuck here. Okay. Now, how do we actually put this into practice? When we run the robust Bayesian meta-analysis in R, we typically follow a structural four-step workflow. So let's work through them one by one along with some practical tips. So the step one is model space setup. So this is where we define our model space by combining different hypotheses for effect sizes, homogeneity, and publication bias. So quick hands up from experience here. Be careful when your choices. Traditional methods like PET, PESC model, it's sometimes very hard for them to converge. Um, but the default select, but the default, the RO, the row BMA function by default they will include this method, this model uh, into the uh, during the estimation. So if you encounter some convergence issue, probably you need to I would recommend you to explicitly specify what kind of publication model you want to include. And second is the convergence diagnostic. The second step is the convergence diagnostic. And because we know that Bayesian method, they relies on Markov chain and Monte Carlo sampling. Uh, so then we need to check convergence. So how do we know our sampler has behaved well? We can check two main diagnostics. So the first one is the R hat, or we know as the potential scale reduction factor in other widely used the statistical software like N+. So we want this R hat to be below 1.05 for all parameters. And the second one is effective sample size, or ESS. We will look for robust ESS values. A safe rule of thumb is that we want to make sure that each samples, each simulation, each sampling chain would have like at least 100 effective samples. And the step, the third step is the hypothesis testing using the Bayes factor. Once convergence is secure, we use Bayes factor to quantify the evidence. So we look closely at the BF effect to test whether a true effect exists, and BF effect to evaluate the specific evidence for publication bias. This will give us a much more nuanced picture than a simple binary p-value. And the last step is comprehensive reporting. So when it comes to writing up our results, we should report the model average point estimates for the overall effect size. And also, when we report the various components, remember that actually what we can find from robust Bayesian meta-analysis, they actually report the total variance and intra-study correlation. So if you want to compute the between study variance or within study variance, you can compute them based on the total variance and the intra-study correlation. So that's all for the robust Bayesian meta-analysis method. And to bring everything together and wrap up our theoretical discussion, let's do a quick comparison of our three main methodological families. So the first one is the regression-based methods, like Egger's test for publication bias detection and PET-PESE for publication correction. So these regression-based methods, they are very fast. They are intuitive, they're universal, and very easy to run. However, as we saw earlier, they are quite vulnerable to high positive rates when dealing with substantial heterogeneity or binary outcomes. And second, we have selection models like the three-parameter selection model. In fact, these models, they are conceptually very powerful because they directly model the p-value publication filter. But the catch is that they typically require a large number of studies, so the K should be very large to converge properly and to attain precise, accurate, and reliable estimates. And also, the traditional frequentist selection models, they struggle when faced with dependent data. And the third one is the most advanced method of today's workshop, that is the robust Bayesian meta-analysis. So while it is computationally demanding, it is remarkably robust. It can seamlessly handle data dependency and publication bias simultaneously. So it can protect our conclusions from being easily undermined. So by weighing the pros and cons of those families, then we realize there is no single silver bullet. Our choice always depends on our data structure, sample size, and analytical goal. And with that, that concludes our theoretical deep dive into advanced bias detection and complex data structures. But we all know the theory is only halfway. So in part three, we will have an hour practice section. Before that, we may take a 5-minute break. So make sure that you have your metaphor and ROBMA packages in store. Let's see you again in 5 minutes. Okay, hi everyone. Welcome back to the final part of our workshop today. In this part, we are moving from theory to practical hands-on R coding. And please open your R Studio and make sure that you have Metaphor and ROBMA packages installed. One thing that I forgot to emphasize is that actually you need to install JAX or just another give sampling that Bayesian software before you can get the ROBMA package to work normally. So if you have all those necessary packages installed, then let's scroll down to part 3 here. Um, to our workshop demo script. So first, let's run the section 0 to load our required packages. So basically, we need Metaphor, this package, and also ROBMA, ROBMA, these two packages to perform our main meta-analysis. And now let's move on to section 1. Load and clean dataset. And actually, this dataset comes from Mertens and colleagues' 2022 PNAS paper on Norgine intervention. And this meta-analysis actually investigates the overall effectiveness of choice architecture interventions, commonly known as notch, in promoting behavior change. Actually, I don't know what they are, but generally they analyze over 200 studies and 400 effect sizes. So the key objective of their research is to evaluate the effect of the interventions. So they use Cohen's d as their meta-analysis effect size metric. So let's load the dataset. And we basically can take a look at the dataset, I think. Oh, where's DF here? Okay, we can look at the dataset here. Um, Actually, we can see we have two columns, publication ID and study ID, these columns. We can see that here, actually, we can see that each publication ID, it corresponds to multiple study ID or effect size ID here, multiple effect size ID. So this means that our data has a hierarchical structure. So the effect size ID is nested within the publication ID. So that means that we have to have a special treatment to handle the data dependency here. And now let's move on to the right of our data set. And we can see that we have the Cohen's d column and the variance d column. So these are the effect sizes and their sampling variance for us to analyze in a minute. Um, um, and here in this workshop, we don't spend time explaining how to compute effect size in different settings. So in this workshop we start from the when you have the sample size and their sampling variances ready, because we want to focus on publication bias detection and correction. Finally, let's take a keep an eye on this variable, the intervention technique variable. And later we will use this variable to subset our data set when we run through a small sample example just in a minute. So then let's close our data set and move on to section 2. Also, we can use summary, this function to take a to look at the summary statistic of each variable and to see if if there is anything strange. Because this is a data set from a published paper, so usually we couldn't find anything weird from this kind of data set. And now let's move on to section 2. And in this section, we will fit a 3-level meta-analytic model to handle the effect size dependency, but we don't consider the publication issue first. So to emphasize that why we need a 3-level meta-analysis model here, because in our data set, one primary study, so the publication ID, often reports multiple effect sizes, actually 2 effect sizes. So the ESID, so this will create the dependency among data points. So now let's look at how we implement the 3-level meta-analytical model in R. So as you can see, we use this function, the rma.mv function from the metaphor package to perform, to fit a 3-level model. And in this function, we use the vi and v, these 2 arguments, to tell the function what are our effect sizes and what are our effect sizes and what are our sampling variances. So here, the Cohen's d, this column is our effect size, and variance d is our sampling variance. And then the third line of this within this function, and this random argument is the core of our 3-level model. It actually, this line of code accounts for the hierarchical structure of our model. So here, the publication ID slash ESID, it means that the ESID is nested within the publication ID. So then we want to separate, okay, the within study variance ESID from the between study variance indexed by the publication ID. And then finally, we use this slab argument to keep track of our study labels for the output. So let's run this piece of code and see what we have from the 3-level meta-analytical model. Okay, let's take a look at the result of the 3-level model. So first, let's look at the variance components part. Here we see how the total heterogeneity is broke down. So first, we have the level 3 variance. So here we use sigma squared 0.1. So this means the level 3 variance, the between study variance. So we have an estimate of 0.13. So this reflects the variation between different studies. And then the second line, the sigma squared 0.2, this reports the within study level, the level 2 variance. So then we will have, for this data set, we have an estimate of 0.01. So this describes the variation across multiple effect sizes within the same study. And then let's look at the test for heterogeneity. And this test, it evaluates the total overall heterogeneity. Specifically, it tests whether the total variance among all observed effect sizes significantly exceeds what can be explained by level 1 sampling error alone. So we can see that the Q statistic here is highly significant. This confirms that our the true effect size varies significantly across our 442 data points. And finally, let's move on to this model results table. And we we get an overall estimate of the mean effect size of 0.4 and a standard error of okay. So that's what we get from a three-level meta-analytic model. Uh, Remember that when we use three-level meta-analysis model to handle the dependent effect size, we actually we only specify the dependency caused by a shared random effect. However, actually, for example, just as in this data set, when we describe the actually the model, we may not describe the covariance caused by sampling error. So for example, for this data set, when we use this V argument, we set V argument to variance D, and we just as we shown when we inspect the data set in a minute ago, we see that this variance D actually is a vector, right? So that means that we do not consider the sampling covariance between effect sizes. But actually, because those data are collected from the same group of participants, then of course they will have sampling covariance. So if you want to guard against the some misspecification here, then probably we can apply, in addition to the three-level meta-analytic model, we can apply the robust variance estimation as well. We can apply this robust RVE method via the club sandwich package. So here we use the robust function, and we indirectly calls for the club sandwich package to perform the robust variance estimation correction. And let's run this piece of code and see what it does to our results. And these are the results from the uh, um, robust variance estimation. And if we look at the R console here, and we can find that actually we got quite similar results. We also have an overall effect size of 0.4, and the homogeneity estimates are almost exactly the same. I think we got quite similar results here because partly because this is a very large data set, over 400 effect sizes and 200 studies. So because of this, the results before and after applying the robust variance estimation tend to converge. And now let's visualize, okay, these results using a forest plot. So basically we use forest function, okay, to plot our results. I think probably let's close the plot here. Let's copy it. In the forest part, each line here represent the confidence interval for individual effect size. And the vertical line here, the dashboard vertical line here, the vertical line basically represent the zero effect line. This is the zero effect line. And we have a small here because this is this plot is too dense. We cannot nearly not notice there is a point here. This this point actually has a diamond shape. And this diamond shape actually plot our overall pool effect size. But we can see from this forest plot that, okay, um, our data points had a substantial spread across studies. And this means we have a high heterogeneity. So we need to explain when we have a large heterogeneity, then we need to explain those heterogeneity. Then how to interpret your heterogeneity? Nowadays, the recommended way to interpret heterogeneity is to use prediction intervals. Okay, we can use predict function to generate the prediction intervals based on our robust three-level meta-analysis model. So basically, we use predict function to generate the prediction intervals for our analysis. Now we have the how to do that. Now we have the um, prediction interval here, and we can see that although we got an average estimate of 0.4 here, however, our prediction interval, the lower limit of the prediction interval is negative 0.34. Uh, so it's lower than zero. This means that although our average estimate is positive and well above zero, however, if you want to do a new experiment, then it's very likely, it's possible that you would get a null result or even a negative effect because the data set shows a high heterogeneity. So that's how we use prediction interval to interpret heterogeneity. There's also other ways to interpret your heterogeneity. For example, some researchers may choose to like we test whether the variance components or the heterogeneity is significant. For example, we may use like ratio test here to test whether the between study variance or the within study variance is significant. But we don't recommend to do that because when you test whether a variance is greater than zero, it's very likely that you would encounter the so-called boundary issue. So basically, the reference distribution or the sampling distribution under the null is not the traditional reference distribution that is the chi-square distribution here. It's actually the mixture of chi-square distribution, and the degrees of freedom of those mixtures are very difficult to compute. So that's the so-called boundary issue. So we don't recommend you to test variance components. But if you like to do that, then you can use the scripts here. The code here we provide you to do that. So that's for the three-level meta-analysis and how you interpret the heterogeneity in the context of meta-analysis. Now let's proceed to section 3. So visualization and Egger's test. So let's first generate a funnel plot first. Basically, we just use the funnel, okay, the function funnel to generate the funnel plot. But because we load multiple packages like the metaphor package and ROBMA package, and sometimes multiple meta-analysis package, each of them have a funnel function. So to avoid confounding with those funnel functions from different packages, we use like funnel.rma to specifically generate funnel plot from an RMA object. So let's run this piece of code. Let me see. Okay, and we have a funnel plot here for our data set. And as you can see, okay, the data points here representing our effect sizes, they are heavily concentrate on the top. And we can see that these data points, they scatter, okay, to the right. And there's a very clear pattern of asymmetry, right? And this visual asymmetry actually suggests we have, first we have high heterogeneity because our data points scatter widely. And the asymmetry actually signals that probably we have potential publication bias. And that's why we need, like, for example, the robust regression test and advanced techniques like selection models and robust Bayesian method to handle the publication bias. Next, let's use the Eggers test, okay, to formally test whether the symmetry of the funnel plot. So first, we need to because in the Eggers test we request effect size on its standard error, but in our data set, actually we don't have standard error. So we need to compute the standard error. So we basically take square root of the variance d variable, and then we save it to SED of our data set. And then we use, and because our data contain dependent effect sizes, so we need to implement the Eggers test within the three-level meta-analysis model. So we still use RMA.MV function to implement Eggers test. And then, but here, what's different from the three-level meta-analysis model? Now we use the modes argument here. So by use modes equals tilde SED, this means that we regress our effect size, so YI, on the standard error SED. So then we can basically this piece of code, we implement the Eggers test within the three-level meta-analytic model. Let's run this piece of code and see what we obtain from Eggers test. Okay, here. As we can see that the coefficient for SED, so the standard error of effect size, is 1.9 around, and we got a very significant p-value, which is smaller than 0.0001. So that means that okay, the funnel plot is highly asymmetric. So this is an indication of severe publication bias. So that's why then we need some advanced method to correct for potential publication bias. So now let's move on to section 4, where we apply PET, PESE to correct for the publication bias in a multi-level framework. So as we introduced in part 2, PET PESE contains two parts. So the first part is PET part and the second part is PESE part. So let's take a look at the first part, PET part. Because the PET part actually it shares the same regression model as the Eggers test. So we don't need to rerun to the model. So we basically pass the Eggers test result to the PET result. But if you do the PET analysis, then we examine the significance of different parameters. So in Eggers test, you look at whether the coefficient of the SED, the standard error, is significant. But if we do the PET analysis, then we actually want to look at the significance of the intercept. Okay, the intercept here. So this intercept means that when we have zero standard error, uh, what is the expected effect size. So here it says that when the standard error goes to 0, then we have a mean effect size of around zero point 0.9. And the p-value is marginally significant, like it's 0.048. So we got a significant PET intercept. And this means that we need to switch to a PTP, a PEESE for a more accurate correction. So we probably had a non-zero mean effect size. So when we have a non-zero effect size, a large effect size, then it's notorious for PET to overcorrect the true value. So that's why we need PESE. So now this piece of code implement the PESE method. So note that here, when we use modes argument to specify our moderator or the predictors in meta regression, here we use variance D instead of SED. So we use sampling variance instead of standard error to predict our effect sizes. So let's run the PESC. And here we can see that the PESE estimate now is point two, around point two. Okay, around point two. And it's very interesting if we compare the result from PESE and the one from the classic standard three-level meta-analysis model. Um, So after the PETPE correction, we get a overall mean effect size estimate of around zero point 0.2. For the uncorrected one from the traditional three-level meta-analysis model is around zero point 0.4. So basically, the correct one is nearly half of the uncorrected one. So from this comparison, you can see how the publication bias, potential publication bias, may distort our estimation. So that's for the PTPESE method. Now let's look at the section 5. So the selection model section. So now we use selection model to correct for potential publication bias. But please keep in mind that standard selection methods ignore the multi-level dependency structures. So, however, they are still widely used, and they are actually being used by the Merton's original PNAS paper. One of the criticism of that paper is that when they performed the publication bias correction, they did not consider the the dependency of the data simultaneously, and so the results they get may not be robust, okay, or accurate. So we will see what we can get from the publication bias correction from the selection model methods. So before we run these. Okay, so first let's implement the standard three parameter selection model, or the 3PSM for short. So to begin with, we need to first feed a standard random effects model to serve as our baseline model or the unadjusted model for 3PSM. And as you can see on the screen, so now we use RMA function instead of RMA.mv function here because the selection model cannot simultaneously handle the dependent effect sizes and publication bias. So that's why we use RMA function here. So we use RMA function to feed the data, to feed basically the random effects uh, um, model, meta-analysis model as our baseline model, unadjusted model. So we can look at the R console here. So the model from the model results table, we see an uncorrected estimate of the mean effect size it's around 0.37. So you can say it's around zero point 0.4, the incorrect one. So now let's run the 50 full three parameter selection model. And we use cell model from the metaphor package to do that. Um, Here we choose not to use the standard weight function from the weight R package for the selection model methods developed by Vivier because and their colleagues because the cell model function is more flexible. So for example, you can decide whether you want to compute a two-sided p-values or one-sided p-values. And also you can choose not to estimate or selection weights, but just estimate a subset of the selection weights. Um, all of those things cannot be done by the standard weight function, R function for the selection model, but you can do that using this cell SEL model function from the metaphor. So that's why we demonstrate this function instead. So let's see how we use the cell function to structure the 3 PSM model. So first, the type argument here. The type, so type equals step fund means that we're modeling the publication selection mechanism using the step functions. And the alternative argument here, by setting argument alternative equals greater, this means that we are computing one-sided p-values and testing for partially significant effects. And finally, the steps argument. Here, it defines the cutoffs for us to set up the p-value intervals. So where the 0.025 and 1 like cut points are the default setup for the step function. So now let's run this piece of code and see what we get from the um, from the let's run it here. Let's see what we get from the fourth 3PSM model. First, let's look at the test for selection model parameters. So this LRT, this likelihood ratio test basically compares, okay, this full 3PSM model with the standard unadjusted model. So basically the model we fit using the RMA function. So here we attain that, okay, this likelihood ratio test is not significant. We got a p-value greater than 0.05. This means they're adding omega weight estimates does not improve model fit. This means this indicates that okay, there's no propagation bias in this data set, which is actually not true. So this you can see this is the limitation, one of the potential limitations of the selection model. You need to be very careful when you specify the cut points for the p-value intervals. By using different cut points, you may arrive at different conclusions. So here, if you use the default cut points, then you attempt that, okay, there is no publication bias. And if you look at the corrected estimate, like it's about 0.3, which is very close to the uncorrected one, so 0.4. So now let's look at what if we believe that, okay, the filtering mechanism or the selection mechanism uh, they do not suppress the negative results. They only suppress non-significant results. Then if that is what you want to hypothesize, then we are actually looking at a two-sided selection mechanism, not one-sided selection mechanism. So by default, the uh, the selection model assume a one-sided selection mechanism. So if we want a two-sided selection mechanism, then we change the alternative argument to two-sided. And then we obtain a two-sided selection mechanism. Here, the p-value would be what the p-value computed is are the two-sided p-values. And if we look at the result from this two-sided 3PSM model, we can see that we attain a very similar results. So this is a way to set up for the two-sided selection mechanism. But here we also show another way of specifying the two-sided selection mechanism. So you can keep the alternative argument equals to greater. So that means that you compute a one-sided p-value and you are looking for positive results. But you can use the delta argument, okay, to only estimate a subset of p-value uh, p-value intervals. So for example, here, we use the steps function uh, to set up three p-value intervals. So the first one is from 0 to 0.025, and the second one is from 0.25 to 0.975, and the third one is from 0.975 to 1. So three p-value intervals. And we fix the first one. So either the p-value smaller than 0.025 or the p-value greater than 0.975 to be the significant p-value intervals. So they all have a publication probability of 100%. So one here, the delta. Delta means omega. So the selection weight, or the relative publication weight. So we fix the publication probability of this two interval to be 1. And the MA for the middle p-value interval, so the interval from 0.025 to 0.975, we set it to an NA. That means that we want this selection weight to be freely estimated. So basically, you will attain identical result from this piece of code above. This is because both of them are we can use different code to specify the same two-sided selection mechanism. And we provide the piece of code here just for you to understand how the alternative delta and steps, these three arguments worked in combined. Okay, that's for three-parameter selection model. So what if we believe the selection mechanism is even more complex? So for example, if non-significant results and negative results have distinct publication probabilities. If in this case, then we may consider a four-parameter selection model by setting, okay, the steps arguments to 0.025 and 0.5 and 1. And we keep the alternative argument to greater, equals to greater. So why 0.5? Why consider this cut points here? Because the negative results have one-sided p-values greater than 0.5. So that means that we allow the function to freely estimate distinct probability, publication probability for the interval, the p-value interval from zero point 0.5 to 1 and from 0.025 to zero point 0.5. So the interval from 0.025 to 5 to zero point 0.5, these this corresponds to the non-significant results, and p-values. So the p-value interval from zero point 0.5 to 1, this interval actually corresponds to the negative results. So we allow these two p-value intervals to have distinct publication probabilities. So let's see what will happen if we fit four parameters selection model. Okay. Let's run it here. So first, let's look at the test for selection model parameters here. This is as we mentioned previously, this is the likelihood ratio test that compared the adjusted model, which is here is the four parameter selection model and the unadjusted model. So basically the model that we attain from the RMA function. So the standard random effects meta-analysis model. As we can see that if we consider a four parameter selection model instead of a three PSM, we get a very significant likelihood ratio test or the chi-square test. So that means that uh, adding the considering the selection weights, adding those parameters into the model, then that greatly improves the model fit. And this is an indication of okay, publication bias. There is publication bias. So you can see if you choose different cut points, then you may arrive at very quite different conclusions. So the 3 PSM tells us that, okay, there is no publication bias, but the 4 PSM tells us that, okay, there's publication bias. So that is the limitation of this method. Okay, so if we believe the underlying selection mechanism is similar to the 4 PSM model, then we believe there is publication bias. And if we look at um, the mean estimate, we can see that from 4 PSM, the overall mean estimate of the nudging intervention is around 0. It's close to 0, 0.06. And we have a confidence interval covering 0. This means that we got a non-significant result. So basically, the cognitive architecture intervention is useless, okay? It does not change our behaviors. So that's what 4 PSM tells us. And if we look at the selection model results here, we can see the publication, the omega weights estimates for individual p-value intervals. So we can see that for the p-value interval from 0.025 to 0.5, the omega estimate is 0.77. This indicates that, okay, for non-significant results, we have around 80% chance of getting published. However, for negative results, so basically the p-value, the omega for p-value ranging from 0.5 to 1, okay, we got an estimate of around 10, 0.10. So that means that for negative results, so the counterintuitive results, so the results that that had a direction that is opposite to our hypothesis. So we only get around 10% of chance, a 10% chance of getting published. So we can see the relative publication probability for non-significant results and negative result, they are quite different. So probably that's why the 4 PSM model gives such a different set of results from those of 3PSM. So which model we should rely on? We don't need to basically make the decision based on our subjective judgment. Basically, we can run a statistical test to do the model comparison. We can see which model fits the data better. So we can use the NOA function here to compare the 3PSM model, so SCM31, and the 4PSM model, so SM4P. Okay, from this model, we have to say that the 3PSM model is the reduced model, and the full model is the 4PSM model, and we can see that the likelihood ratio test tells us that the full model is fit the data significantly better than the reduced model. This means that the 4PSM model is the better model. So maybe the frequentist method tells us that we should rely on the 4PSM model. But the 4PSM model returns us with a null defect. So the intervention does not change our behavior. So that's what 4PSM model tells us. And we have fully shown, okay, how to run the selection model. And now let's move on to the second part of section 5, that is the Vivier-Woods sensitivity analysis with a fixed weight. And we all know that if we have analysis. So here we consider two selection models or two selection weights, two sets of selection weights. One actually here represents the moderate publication bias. So we can see that for the p-value intervals with the for the negative results correspond for the p-value interval correspond to negative results, we still have around a 50% chance of getting published. And the other one is the severe selection model. So for the negative results, we only have around 10% chance of publication. So we can use the cell model to perform the fixed weight sensitivity analysis. So how to do that? Basically, we just assign those pre-specified weights, those weight factor to the delta argument in the cell model function. And then they will perform, instead of fitting the selection model, they will perform the fixed weight sensitivity analysis. So here we fit the moderate selection and the severe selection. We can see what we'll get from. Oh, okay, I didn't specify the weights first. That's it takes a while because probably because we because we consider so many coupons, so many p-value intervals, so it needs time to handle those p-value intervals. basically now we already get the moderate selection model result. It really takes time. Okay, now we got the results. So first, let's look at the moderate. Let's see. Um, let's see the moderate selection model result. And for the moderate, so if we consider moderate publication bias, then the corrected mean effect size estimates around zero point 0.3 here. And however, if we consider severe selection or severe publication bias, then the corrected estimate becomes drops to 0.07, nearly zero, and actually it's not significant because the confidence interval includes zero. And as we discussed in part two, we mentioned that, okay, when we perform sensitivity analysis and we find that, okay, um, we can get quite different results from by considering different level of publication bias. Then this is an indication of non-robustness. And in this situation, we cannot simply ignore it. We have several options to for us. So probably we can check. We can we can check whether our data we have the issue of data sparsity or there is any overfitting issue. And then, but this is probably not the case here because we have a large data set. And also we can report exactly, okay, the level of publication bias required uh, to 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 invalidate our findings. For example, when we consider the moderate publication bias is present, we still have a very large or moderate effect size, which is around zero point 0.3, a significant effect size. But if we consider there is a severe publication bias, then the intervention probably has no effect. So we can report the exact level here is the severe publication level of bias would invalidate our findings. And also, we could explore alternative specifications, like we can consider incorporating additional moderators, like or predictors in meta regression. And next, let's move on to the last part of section 5, where we look at a very common practical issues that's the small sample estimation and convergence warning. And basically, we use the intervention technique, this variable, to subset our data. And then we run the four parameter selection model. And for this subset of data, we have 19 effect sizes instead of 400, over 400 effect sizes. And we will see what would happen here. We got warning messages from the cell model function. It tells us that one p-value interval does not contain any observations. This means that the results from this small sample data set are unreliable and not trustworthy. So here we just want to show you the small sample issue that you may encounter. And next, we will show how to use the robust meta-analysis technique to handle those small sample issues. So let's move on to the last part of our today's workshop. That is the most advanced meta-analysis technique. That is the multi-level robust Bayesian meta-analysis method. And this method can solve, okay, all the issues like the dependent emphasizes, publication bias, heterogeneity, small sample, and all those issues they can solve at once, all at once. And we basically use the ROBMA function from the ROBMA package to implement this method. Now let's look at how this function is structured. So first we use these two arguments, yi and vi, okay, to tell the function uh, which is our effect size vector and which is our sampling variance vector. And also we use the measure argument here to tell the function that, okay, here the effect size is the standardized mean difference or the current state here. And I want to stress here that is to handle dependency, we use this Gloucester function. Okay, this Gloucester function here by setting Gloucester argument to publication ID, then this is to tell the ROBMA function, okay, you need to group the dependent emphasis by publication ID. In this way, they will set up a three-level meta-analysis model instead of a two-level model to handle the effect size dependency. And then if we want to handle the publication bias issue, actually by default, they will include like, I think six or maybe six different publication bias model here. But if you want to specify if those publication models do not fit your research interest, then you may explicitly specify what kind of publication model you want to include it here. For example, here I want to include the one-sided selection model with uh, uh, one with one cut point that is 0.025 and the other one with two cut points 0.025 and zero point 0.5. I want to consider basically these two selection model correspond to the 3 PSM and 4 PSM considered earlier I think in the selection model section. So I want to cross-check the publication bias uh, cross-check with the selection model results. So that's why I explicitly specify the selection model here. And you might note that I actually comment the priors for the PET and PESC method. This is because for this data set, these two models does not converge, and it would bring in the convergence issue. So that's why I comment here. And by specifying like multiple publication bias model, basically the this ROBMA function they will average across those publication bias models using the Bayes model averaging, and this will give a more robust and balanced results compared to the frequentist selection model methods. So let's run this piece of code for the wait a minute. So hard for me to okay. I think it would take so while to run the robust Bayesian meta-analysis because it's time consuming, computational intensive. But but before we get the result from this function, we can introduce what we will do next. Actually, after we get the result from the rho BNA function, first need to check the convergence. So we can first we can visually check the convergence. We can use we can check the convergence using the trace plot. And to generate the trace plot, we can use this plot diagnostic trace function. And in previous rho BMA package, you can directly use the plot function to generate the trace plot. But in the newest version of this rho BMA function, you cannot use that. You no longer can use the plot function to generate trace plot. And it's very important for you to check convergence for Bayesian methods because if the MCMC chained the sampler does not behave well, then the results are not trustworthy. Why did it take so long? And here we use this chain argument to specify, okay, the number of chains that we would like to consider. Okay, we're done. Now we get the result. Let's look at the trace plot of individual parameters. So for example, let's generate the trace plot for the mu parameter or the mean effect size parameter. Okay. Here we got this trace plot of the of the mu parameter. And this plot actually shows the MCMC sampling chains ranging from 0 to 5,000 iterations after the burn-in period. And notice that, okay, the different color chains thoroughly mixed together and fluctuated around a stable central band, ranging from around 0.25 to 0.4. And this is a side. There's no side of, for example, the sticking, chaining, or divergent transitions. And this this means that okay, those different chains they mix well together, and then this gives us a high confidence that our MCMC sampling has successfully converged, meaning our posterior estimates for the mu parameter are reliable and stable. And actually, we need to examine, okay, the trace plot for each parameter one by one. But because of the time constraint, we don't do that in this workshop. But when you do the actual meta-analysis, you need to go through the trace plot for each individual parameters. Now, let's look at the final report from the ROBMA function. Let's first look at the estimate table. So we need to first check the convergence using the two metrics we mentioned in part 2. So basically the R hat or the potential scale reduction factor. So this R hat, we need R hat for all parameters to be smaller than 1.05, which we can see that our data set satisfied this rule of thumb. And also the effective sample size, that is ESS here. We want ESS to be greater than 400 for this data set, for this analysis, because we have 4 chains. And then for each chain, it is recommended to have at least 100 effective sample size. So here, the ESS for all parameters are greater than 400. So then we are confident that the MCMC sampling has successfully converged. So we can now dive deeper into look closer uh, at our the parameter estimates and other results. So for example, let's look at the component inclusion table. And we can see that the inclusion Bayes factor for all um, components, like for the effect, so basically the mean effect, and for the homogeneity, so basically the total variance here, the total standard deviation, okay, not the within or between the total standard deviation, and for the publication bias, okay, all of them are extremely large. This is an indication that this means that there is overwhelming evidence for the presence of true effect, homogeneity, and publication bias. And then we can look at the estimates table. Uh, we can see that the Bayesian corrected overall effect size estimate is about 0.3, okay, which is close to the uncorrected three-level meta-analysis model or the 3 PSM corrected estimate. And we got an estimate of homogeneity or between study standard deviation uh, around 0.4. So this is the total standard deviation, okay? You can square it to attain the total between total homogeneity, which is around 0.16 by 0.16. And the last one, the row, this is the intra-study correlation. So basically, we compute this correlation by dividing the so we divide the between study variance by the total variance. So then we can use this total standard deviation and the intra-study correlation to compute, okay, what is the within study variance and the between study variance. And finally, let's look at the publication bias table. And we can attain here, we can look at the relative publication bias relative publication probability estimates. And we can see that for non-significant results, so for this interval, we the robust Bayesian meta-analysis tells us that probably we got around 60% a chance of getting published. However, for negative results, so for the last interval, then the publication probability drops to around 40%. So, well, for the omega estimates, for the selection weights estimate, the Bayesian method provides are closer to that from 4 PSM. But for the overall mean effect estimate, then it's closer to the 3 PSM, frequentist 3 PSM. Why this happened? Originally, I think probably this is because, okay, the model averaging part. So the model averaging probably uh, make this happen. However, after I inspect the posterior model probability, then I find that the discrepancy between the frequentist selection model and the Bayesian selection model method is that actually because the frequentist selection model method they ignore the data dependency so that they get a underestimated overall effect size estimate. So for example, here, the summary model function produces the uh, posterior model probabilities for each model considered in the Bayesian analysis. So we can see here that from this table, we can see that actually in total, the rho BMA function consider 12 models for our meta-analysis. And for the first 11 models, okay, here you can see the post probability column. Uh, the post model probabilities are zero. And for the very last model that contains non-zero, that assumes a non-zero mean effect, true heterogeneity, and also for selection model, for parameter selection model, the posterior probability model probability is one. So that means that um, the ultimate Bayesian estimates, Bayesian results are solely based on the 4 PSM model. So then the discrepancy between the Bayesian results and the frequentist 4 PSM results are due to solely probably due to the ignorance of the data dependency. So we can see that if we ignore the data dependency, maybe we can underestimate it. We may underestimate the true mean effect. So that's great for our data set because if we apply the frequentist selection model, we'll obtain a null result because the average corrected average mean effect size is close to zero and not significant. But if we use the Bayesian method to considering um, the dependency of effect sizes and the publication bias issue simultaneously, then we obtain an average effect of around zero point 0.3, which is still significant. So that's very good for researchers. So then you and finally, let's look at the how the Bayesian method solve the small sample issues. So um, so here we try to use the rho BMA function to fit the subset of our data set. That is, we only the subset of the data set only contains 19 effect sizes. And for this data set, actually the rho BMA function can return can still get a results. And then you can so from this example, you can see that how the Bayesian method stabilize the estimation process. Okay. And I think that's bring us to the end of today's workshop. And for today's workshop, we have walked through from the three-level meta-analysis and aggregates test to PET, PESE, and selection model and robust Bayesian meta-analysis. And and thanks very much for you joining today's workshop. And I really appreciate your attention and engagement. And that's all for my workshop. And I think because we are running out of time, and so probably we don't have a Q&A section. So if you have any questions regarding today's workshop or the meta-analysis in general, just drop me at the email. So here is my email. Oh, wait a minute. Where is email? Okay. You can contact me using this email address, and I will be happy to help. And that's it for today's workshop. Any questions? Thank you, and bye-bye. Have a nice day.
Goodbye
Bye-bye.
and thank you.